Okay. Now, which basic functions are one-to-one? First of all, let's go to this one, because some of you got something a little bit backwards, but did a really nice job on it, okay? And you want to get it turned around. So is this a one-to-one function? Okay. Is this even a function? Okay, so it's not a function. Why is it not a function? Because of the vertical line test, right? Because for given x value, let's just take x here. You can't answer the question, what's f of x? Is it this or this or this or this, right? So you project this point over here, project this point over here, you project this point over here, you project this point over here, you get four answers. You get four values of y that correspond to that x. It can only be one. Okay. So implicitly, this means a function that isn't one-to-one. And that's a little bit implicit. So, this certainly isn't one-to-one, but it's not even a function. But a function that's not one-to-one, turn that over to the side. There's a function that isn't one-to-one because, or let's say this y value, you have several values of x. That's still a good function. Passes a vertical line test. There's just one y for a given x, but there are many x's for a given y. Okay, so I'm going to say this. Many y values for a given x, so it's not a function. No, I didn't have room to write out function. I wasn't smart enough to start over here. I think you see what that means. Okay. Down here. Many x values for given y, so it's not one-to-one. But it is a function. So you want to be clear on that because it's going to become important and we're trying to do inverse function. Okay. Table for a function that is one-to-one. I can make a short table, and there are many ways to do this. We've got x and y equals f of x. So let's say x is 1, 4, 7, 11. For some reason, we want to use these four numbers. Take any four numbers. You can't use the same number twice over here because if you did, it wouldn't be a function. Okay. At least if you had two different y values, it's the same maximum. Okay. So over here, let's say y is 3, -12, 586, and -15. Well, those are probably the values you chose, aren't they? Everybody would have chosen those values. Yeah, right. Okay, so you choose any values you want here as long as they don't repeat. Okay, this is 1 to 1. Okay, now here's another one. Let's go ahead and use the same X value so I don't have to think for it. Okay, and let's let you have X equal, oh, I'm gonna use some of the same. Except it takes too long to write out 586, so I'm just gonna write 3 over here. Okay. Well, is this 1 to 1? Well, it's not 1 to 1. We've got 2 X values for Y equals 3. Still a function. Because all our X values are different. It's not 1 to 1. Make sense? Okay, good. Okay, just found that I apparently didn't record my explanations here. So I'm going to do that kind of quickly. In the meantime, I'm asking everybody to write down these and circle the ones that are 1 to 1. Then we'll come back and answer that. We'll move this over a little bit so I get this whole board on the screen. Okay. I started by sketching graphs because there's a little confusion on some of these graphs. Some people drew a graph that looks like this, and that's pretty good. If you'd have drawn it like this, it would have been a function that isn't 1 to 1. Now, why is it that this function is not 1 to 1? Or why is it that this is not a 1 to 1 function? Okay, because we want one that isn't 1 to 1, meaning a function that isn't 1 to 1. Well, it isn't 1 to 1 because it isn't a function. There are many Y values for given X values, so this is not a function. Now down here, if we drew something like this, there are many X values for given Y. Okay. Now up here, we see the given X value here. You see 1, 2, 3, 4 possible Y values. Down here, we draw this dotted line that corresponds to a single Y value, whatever Y is at this point. That's the value of Y everywhere on this line. And there are 1, 2, 3, 4 X's for which the curve intersects that line, meaning there are 4 X's that have that correspond to that Y value. So it's not 1 to 1. There's not just one Y value for every X. Okay, now we'll talk more about that idea in a minute, but we ended up with some contrasting things there. Okay, so let's make a table for a function that is 1 to 1. So I just made this table. Why is this table 1 to 1? Well, all my X values are different, meaning it is a function. But none of the Y values are the same. So every X has its own Y value. It's 1 to 1. There's 1 X for every Y. And I think it just said something backward. There's just 1 X for every Y value. There's only 1 X. Anyhow, over here, so it's a function. This function, these are all the same values over here, except I got tired of writing 586. That's too big. Takes too long to write, so I wrote 3 here. Well, that messed me up because that's no longer a 1 to 1 function. It's still a function. Okay, it's a function because there's only 1 Y value for every given X. But it's not 1 to 1 because there are 2 Y values two x values for y equals 3. So y equals 3 occurs twice in a similar way to whatever this y value occurs for 4 different x values in this graph. Now, again, there's a question of related to whether this is a function. And it is a function because, again, you have only one y value for any given x, but you have 2 x values for this y value, so it's not 1-to-1. Over here, this isn't a function at all because I've used the same values except my 11, I wrote a 1 here. So now x equals 1 gives you 3, but x equals 1 also gives you negative 15. A function can't do that. So there are 2 y's for x equals 1, not a function. Okay, well, we'll come to the question, which basic functions are 1-to-1. So here are the basic functions. And I got partial answers to this question, but I didn't get a full answer. So I ask everybody to write these expressions down and circle the ones that define 1-to-1 functions. Okay. So some people wanted to go ahead and make the table. That's acceptable at this point, but you really want to kind of have these tables in your head for at least these 5 functions. I think you should be able to make the table. You should be able to write down these 5 most basic functions, okay? Make the table and sketch the graph in a minute or less. The graph, well, it's a minute per graph, okay? So in 5 minutes, you ought to be able to write all this down, okay? And I'm not going to do that, but I'm going to show you the shapes. What's the shape of this graph? It's a graph. What's the shape of this graph? It's up like this, levels off here, comes back up, unlike what open math shows you, where this thing goes through the origin at an angle. It's flat for an instant at the origin, gets very flat. And if you go back to the way we talked about functions last week, every time you move twice as close to the y-axis, you get 8 times closer to the x-axis. So that flattens this thing out really fast. And then it takes off really fast. And well, anyhow, 1/x, the graph looks like this. Not very well drawn. 1/x squared. Graph kind of looks like this, doesn't touch the x-axis. Just slotting them down here. Like the little things that aren't right, but we'll get it right. And the exponential function looks like this. You got to have those pictures in your mind, know which formula goes with it, and understand why the arithmetic gives you that shape, okay? If you understand those 5, well, the assignment for today had a bunch more. Okay, it had a square root function, absolute value function. I think it might even add a step function. Okay, those are important functions. But if you understand these, it's not hard to understand all those extras. So we're just confining what we really want to know at this point of the course to these 5 functions. And they're the ones that come up most commonly. The others are important. These are, in a sense, the most important. In my opinion, anybody that has an opposite opinion is wrong, but I respect them anyway. Okay, not really. I mean, they're not wrong. As long as it's a well thought out opinion, I can respect it, whether I agree with it or not. Okay, so which of these are 1-to-1? Well, if you visualize the graphs, if you know what the graphs look like, you can circle them instantly. This here, this here, and this one. This one isn't because here's a y value along this line, and here 2 x's can have that y value. A horizontal line test, but you don't want to just memorize horizontal line test. You want to understand that the horizontal line test answers the question. Okay, are there y values that correspond to more than one x? Takes a little time to sort that out and make that intuitive and natural. So you want to think, and here are the same thing. There's a y value, here are two x values. Up here, doesn't matter what horizontal line you draw, get different x values. Same here, same here. So those are your one-to-one functions. Domain is your set of all possible x values. Okay. Among the basic functions, that are the most basic functions, we confine ourselves to the x interval from -2 to 2, just the way you've graphed them. So what are the possible x values for y equals x squared? Well, let's talk about that for a minute. Okay, so the question is, got f of x equals 1 over x minus 3. What x values won't work, if any? And just to make sure we have the context. Here are our basic functions. This one, and this one are one-to-one. This one and this one aren't because they're given y value here, there are two x values. They're given y value here, there are two x values. For the others, for any given y value, exactly one x values. Now, what's the domain of a function? Okay, set of all possible x values. For example, basic squaring function, which is defined between -2 and 2. If we make a table, the domain is all the x values, just a set of x values. We talked about this last time, so it's kind of a quick summary, just to remind you. A domain set of all x values, the range is the set of all y values, and here's the set of all y values. If we do the extended basic function curve that we get, if we connect these points, and if it's done exactly right, the domain would consist of all x values from -2 to 2, because if we take all the points on the curve and mark their x values, we're going to get every number from -2 to 2. There's always an x value for every point of the curve, so the domain would be from -2 to 2. The range would go from 0 to 4 because the range is a set of all y values. The y values go from 0 to 4. And if we take all the points here and find their y values, we get all the numbers from 0 to 4. There's nothing missing. Now, talked about that in more detail last time, so review it if you need to. It's going to be important for code. Assign. So if we've got this function, f of x equals 1 over x minus 3, are there any x values that we can't use in that function? You had a minute to think about it. Okay, got a couple of good quick answers there. X after 3. That's undefined. Does not exist, so you can use DNE if you want, which is what the math wants you to use. Okay, that's what it recognizes. Give it anything more complicated than that, it won't know what it's looking at. Okay, so any other x is okay because any other x is just 1 over some number that isn't 0. So domain is the interval from negative infinity to zero, union the interval from zero to infinity. Oh, it's not 0 is 3. Now, we saw this notation in relation to the reciprocal function last time. So you might want to review that for more explanation. But we did that last time. And you're going to see it. OpenMath is going to explain it to you again if you still don't get it. Okay. So either review what I said last time or take a good look at OpenMath. Videos will guide you. Okay, so there's your domain. The range well, if you think about it, if you divide 1 by any old number other than 0, you're going to get a result. That's while we're in the domain. If you divide 1 by a really big number, you get a number that's close to 0. If you divide 1 by a negative number, you get a negative number. If you divide 1 by a really small number, you get a big number. Maybe positive, big, maybe negative. Okay? That makes sense? So for that reason, and OpenMath will give you more explanation. The range is, now there's only one number that you can't get. What number can't you get if you divide by dividing something into 1? No, you can get 3. Okay, if you divide 1 by 1/3, go back to your fractions. 1 divided by 1/3 gives you 3, right? But you can't get 0. Okay. There's no number that divides into 1 and gives you 0. Every number goes in at least a fractional number of times. So the range is negative infinity to 0. Means 0 to infinity. What about u of x equals 1 over x minus 3 quantity squared? How does that differ? Are there values that won't work? Can you do your finger show me a value that won't work? Any number you can't plug in here doesn't work. You can't plug in 3. Because again, it gives you 0 in the denominator. 0 squared is still 0. Okay. Now, are there any other numbers that you can't get when you do this? Okay. So again, 1 over x minus 3, x can't be 3, because if x is 3, you're dividing 1 by 0. Any other value of x is okay. The domain goes from negative infinity to 3, and from 3 to infinity, but you have to exclude 3, and that's how you do it. And we'll reinforce that explanation. The range, if x minus 3 is really big, then 1 divided by x minus 3 is really small. So you get really small numbers. But you can't get 0 because x minus 3 is never that big. Okay, any number will go into 1 some number of times, even if it's a tiny fraction. So you get any number down to 0 by making x minus 3 big. And you can get any number up to infinity by letting x minus 3 be small enough. Small enough it'll go into 1 a whole lot of times. That's the intuitive way to do it. And of course, x minus 3 could be positive or negative, depending on whether x is If X is bigger than 3, it's going to be positive. If X is less than 3, you're going to get a negative when you subtract 3 from it. That means that you can get any number from the tiniest to the biggest, and it can be positive or negative. So the range is negative infinity to 0, 0 to infinity. Now, if you go to this one, it gets a little trickier. You got to do a little more algebra, and I did some algebra here. If you don't understand the algebra, it's kind of okay right now, but might need to do more with that. Let's see how you do in the homework. Again, though, X can't be 3 because that gives you 0 in the denominator. The other thing is, X minus 3 squared is always positive. You divide 1 by a positive number, you get a positive number. Okay. Now, X minus 3 squared can be as big as you want or as small as you want, but it's always positive. If it's really big, you're going to get something close to 0. If it's really small, you're going to get something really big. The result is that your range goes from 0 to infinity, or your domain is still the same as the domain of this one. So the difference between this and this is you have a square here, which makes the denominator positive. There isn't a possibility of getting negative numbers. So X minus 3 squared is never less than 0. So the reciprocal of X minus 3 squared, if you can read that, is always greater than 0. In other words, always positive. So there's your range, your domain. Okay, other restrictions on domain and range, and they're really only a couple. One of them is your denominator can't be 0. Okay, that restricts your domain. Range can be a little trickier. With range, you can get into some serious algebra. Let's try this. H of X is the square root of X minus 4. Now, can you give me a number that you can't plug into that and get a real number? Okay, so we got a couple of possible answers. So I said 4. Well, 4 is close, but if X is 4, you get 0 in here, and the square root of 0, what do you multiply by 0 to get 0? 0. 0 times 0 is 0, right? So 0 squared is 0. So the square root of 0 is 0. Okay. Now, the one thing you can't get, and somebody observed this, is you can't get a negative number out of it. Okay. So your restriction square root of a negative isn't a real number. So that's the other big restriction that you have on domains with functions that are given by equations and formulas. And that's a lot of what you're going to see. Okay, square root of a negative isn't a real number, so that X minus 4 can't be negative. Well, you conclude that X has to be at least 4, because if X is less than 4, if X is 3, 3 minus 1 is negative 1. If X is 3.99999, X minus 4 is still negative, right? Any number less than 4 will give you a negative. The domain is then for infinity. Of course, 4 is included, as we just said. Okay. Kind of makes sense. It'll make more sense when you get into the assignment. you see the way to write these things out and so forth. But there's your domain. Your range, I don't have room to write what the range is, but if X is bigger than, greater than or equal to 4, then you can get any number here from 0 on up. So the square root could be any number from 0 on up. Okay? So the range is all positive numbers. The interval 0, infinity, or zeros included. You can get 0. You know that because you told me in your first attempt was 4, but we saw that the square root of 4, a square root of 0 is 0. And there's more to the argument. Comes down to this. If you have a function given an algebraic expression, first two things you expect, there are other things, but the ones you're going to run into here are make sure your denominator can't be 0, eliminate any values of X that makes the denominator 0. And if you have a square root, eliminate any value of X that gives you a negative under the square root. Not too hard to get used to that. Now, if we get into the algebra here, then you got to have a few algebra skills. And if you need that, let Open Math show you step by step. And if we find that you're having trouble with that, we'll do that, a lot of that step by step next time. Okay. And you can always email me too, send you back an email that explains it. Okay, so 3 big things are coming up. Rate of change, because it's a central concept in first semester calculus. And if you're in this course, it's often because you're in a curriculum, it's going to lead you to an applied calculus course. Okay. This course should prepare you well for that. Well, they're doing real well, so I think it's going to be good there. Rate of change. Then we have composites functions. And these two at least are coming up next week, and then transformations. You take this and this with your basic functions. So you do compositions of basic functions, you get new functions. You transform basic functions, maybe do compositions with them. Those are all the functions you're probably ever going to have to worry about in your life. Okay. The compositions and transformations, the basic functions. Not just the 5 basic functions, although that's probably 90% of it. The other functions, which are easy to understand if you understand the 5, as I've said, give you pretty much a full range of functions that take you all the way through an engineering calculus course and a differential equations and a multivariable calculus course. If you really fall in love with mathematics, you might want to do that. Engineering is a great field, but that's not where most of you are headed. Okay, you are headed places though where you need to be able to understand these combinations of your basic functions, which is why I stress these basic functions as much as they can be stressed. Okay, well, we're not going to talk about this today. We'll talk about this next week before we have that assignment. I'm not going to talk about composite functions until the assignment is coming up. But we are going to talk a little bit about transformations because they give people more trouble than the other two. And we want to start talking about it early. Okay, so all I want to talk about right now is what it means to move a point to the right or left, to move a point up or down, These are easy concepts. I don't think you're gonna have any trouble with this. Okay, and to move a point so many times further or so many times closer to an axis. And we've already seen that. So you should be well prepared for the assignment that's due on Monday. So let's just think, let's take a point. Let's just take your point A. Let's call it P, the point. So I can say move P. Two units to the right. Then 3 units down. Then twice as far from the x-axis. So take a minute, we got 5 minutes left. Give you about 2 minutes to just slop down a graph, label your point A, B, and show me what happens. Almost out of time, so I'm going to go ahead and do this. If you didn't understand what to do, I think most people did. It should be clear after I do it. So, okay, so I got to move this point 2 units to the right. So that means 2 units. So 2 units is this far. So 2 units to the right means, of course, my x coordinate is going to increase by 2. So now the x coordinate is 4, and this point is 4 up and 4. Everybody understand? Pretty simple. Okay. Now, that's really tough. I got to move it down 3 units. Okay. Well, it's up here at 4. If I move it down 3 units, that's going to put me at y equals 1. So now the coordinates are 4, 1. Okay. Then I've got to move it twice as far from the x-axis. Now, we did this last time, moving things twice as close and twice as far. So it should be pretty obvious what to do, but just in case. Well, this thing is now 1 unit from the x-axis. If I move it twice as far, it's going to be 2 units. Okay, so that's going to move it from here to here. So the point would be 4, 2. Any question about that? Now, if you do that with every point of a graph, you're going to take the whole graph and all the points are going to move 2 to the right. Is your graph going to change shape? No, it's not going to change shape. You're just going to grab the whole thing and move it 2 units to the right. Then you can move it 3 units down, it's still going to have the same shape. Now, if you double the distance from the x-axis, that changes the shape. Makes the graph narrower. Okay. It stretches it out twice as far in the y direction. And hopefully that makes sense. Now we'll go on with that idea, and the assignment just picks up on those ideas. If you understand that much about one point, then you can do it with a bunch of points. Okay? And you can see how the shape of a graph changes when you stretch it, when you move it twice as far, twice as close. Okay? But it doesn't change if you move it right or left or up or down. So I don't think you're going to have too much trouble with that. If you do, email me. I'll try to clarify it for you. Okay?